So it's almost 9 a.m. Depending on where you are. So I think it's 9 a.m. in New York. It's probably about 8 p.m. in Bangalore, and it's midnight in Sydney. So we'll just give everyone another minute before we start, and then we'll kick off with our presentation on MessageBroker, our MessageBroker plugin, SonarQube, and the other tools we've developed. So it's a few minutes past 9, so we'll just kick off. So I'd like to firstly thank everyone for joining us or joining me in this presentation. Hopefully you'll, whether or not you're interested in our product, you'll at least get some a few ideas and a bit of food for thought, and some a little bit more information and a few more thoughts around code quality and the Sonar ecosystem and toolset. So we'll just quickly go through the agenda. So we're just going to talk about what we're trying to achieve, and then we'll follow that with a demonstration of the product running and the reports it produces, and then we'll finish up with some questions. So depending on how we go, it should take maybe 40 minutes. So what are we trying to achieve with this product, and what are we trying to achieve with products like SonarQube? So lots of people probably have different ways of putting this, but the way I like to think of it is we're trying to write cheap code. Now, but lots of people have different thoughts on this. When I say cheap code, I don't mean we're going to hire the cheapest developers we can find, and we're going to give them the worst hardware we can possibly find, and work them 12 hours a day with no air conditioning. What I mean by cheap code is cheap that's code that's easily changeable and easily maintainable, and has a low cost of ownership. So what do I mean by cheap? So bug-free. Obviously, code that doesn't do what it's supposed to do is more expensive than code that does what it's supposed to do. And this may mean code that doesn't do what it's supposed to do may not be able to handle customer requests, and you may lose customers. Or worst case, code that dealing with insurance or banking products could actually cost the organization a lot of money if it miscalculates an interest rate or something like that, or doesn't settle a trade correctly. Now, talking about maintainability and being able to extend and understand the code, it needs to be understood. The more complex the code is, the harder it is to understand. So the more time it takes, the more experienced your developers are going to have to be to understand the code and make changes. So the quicker you can change your code, the more effective it is in the business sense, and the more value for money you're getting from your code. So what we're talking about there is not just cheap to maintain from a development perspective, but cheap to maintain and value for money from a business perspective. Performs well. So code that doesn't perform well might just mean that your users have to wait longer than is required. In the case of customer-facing systems, you might potentially lose customers. In the case of other environments where you have to share hardware or share resources, it actually might make it operationally more expensive if you have to actually purchase more hardware because your code is underperforming. So this is getting back to maintainability. So code that can be changed easily is more valuable and cheaper than code that takes a lot of knowledge and background to change. Copy-paste detection. So what we're talking about here is code that is replicated, or code that has the same piece of functionality in different places. is going to be more costly to change than code that has potentially a centralized function. So if you have a function that says, one centralized function that says calculate current interest rate and returns a value of 7%, or calculate LIBOR and returns a value of 3%, you've only got one place where that calculation needs to be tested, and one place where that calculation needs to be fixed or changed or modified. If you've got 27 different calculators for LIBOR in all sorts of different places in the code, then when you want to change your LIBOR calculation, you have a whole lot of different places to change, which is expensive, and you've got a whole lot of different places to regression test. So code that can also be tested is cheap. So the easier it is to be tested, the easier it is to build automatic testing, and the easier it is to build regression test suites, which means the quicker it can be changed and the cheaper it can be changed. So a system that's easily tested and has a good suite of unit testing and automatic regression testing is going to be cheaper to maintain than a system that requires mostly manual testing. So does anyone have any questions just before I go on with the next few points? Okay, and the last point here is knowing what you're testing. So if you know your coverage, if you know you're testing the whole system as part of your regression test, then you can be comfortable changing your code. And if the regression tests still work, then you have a lot of confidence that the code will still function. If you actually have a very small percentage of your code being automatically tested or being unit tested, then you don't really have confidence that you've changed the system safely without breaking something else. So how do we get to good code? There's a few thoughts around this. There's an article from CERN-IQ developers, and it talks about the 7 deadly sins of software development, and talks about finding and looking for bugs and potential bugs, maintaining code standards, preventing duplication, making sure you've got enough unit tests, making sure you're writing code that's simple and not too complex, and so it's easy to change. Poor design, well, we can sort of leave that off the list for the moment. And not enough or too many comments. We can kind of leave that off as well. Okay, so when I'm talking about unit testing, definition of unit testing here is components of your system that can be tested in small parts. That's a bit frustrating. So we're talking about unit testing. We're talking about small parts or small components of your system that can be tested, and this can extend out to larger modules that can be tested. So we think of our product as Find Bugs, Checkstyle, and PMD, but for Message Broker. So if you're not coming from a Java background, Find Bugs is an open source product that essentially looks for common programming practices that people should avoid, and essentially anti-patterns. So Find Bugs itself checks for all sorts of different potential defects and reports back on them. So what we're doing was simulating that sort of product. Checkstyle is another open source product, mostly in the Java world or the Java space. And essentially Checkstyle is a product that allows you to check that your code is conforming to your standards. And so you can pick and choose which standards are important, and then that will help to maintain standards in your code. So it reports on where your developers have deviated from your standards. So the standards might be naming conventions on methods or naming conventions on variables, ensuring that each procedure or function or method has a comment block, make sure that your header files have a certain comment block, and a few other things like that. PMD is very much like Find Bugs, and it just has a different set of bugs it finds and coding conventions that it checks for. And the last term the last term in that sort of space is something called technical debt. So technical debt is a term coined by, I believe, by Martin Fowler, and talks about how to explain bad code to a business person. So essentially, when we're talking about technical debt, we're saying this bad code in our system incurs essentially a backlog or additional complexity or bad functionality or bad coding practices that make it harder to move forward. So essentially, when we think of technical debt as a system, technical debt is anything that prevents us from developing code as most efficient as we can. So if we have a lot of code which isn't being called, for example, dead code, then it's a bit more difficult to change or create new code if you're not sure which parts of the code is being executed and which parts of the code isn't. So you might spend some time adding functionality to a piece of dead code that never gets called, for example. So so what we're trying to do with Sonar and MB Precise plugin is firstly measure our technical debt, measure how many potential defects, where we deviate from our standard, where we haven't got unit testing, and then from that we create an action plan of how do we remove the technical debt, how to limit our technical debt to help our developers move forward in the future. So continuous integration is a practice where all the source code from all the developers is compiled together in one place in a regular interval to make sure that all the components, all the functions, all the features are worked well together. So what this prevents is one team developing code to a certain standard with a certain API, for example, and then another team developing another piece of code with a slightly different standard, but they thought they were talking about the same thing. And lo and behold, a couple of months later, when they put the code together to try and test, they find they get a lot of defects because the systems aren't talking to each other, or the components from the system aren't talking to each other. So continuous integration is a practice where we merge our code together as often as possible as developers so that we can make sure that we're all talking the same language and all the components are talking together. And there's another term called continuous delivery. And what we're talking about continuous delivery is where our code is integrated regularly and where we know we have a certain amount of quality in our code that we can deploy our code into an environment and test it reasonably quickly or quickly and regularly so that we can release it to our business for testing or to our business for verification regularly. So what this means is we can develop a lot more code within the agile practice of design a bit, or analyze a bit, design a bit, code a bit, deploy a bit, test a bit, verify a bit, and then go on to the next feature. So we get these quick cycles, or helps us create quick cycles and quick feedback with our business users. And the last one, Snowflake setups that I'm going to talk about. Snowflake setups is where systems or components are put together in an environment, and the next time they're put together in a different environment, they're slightly different. So we say Snowflake because two snowflakes are the same. And so what this means from a DevOps point of view, or from a release management point of view, is we want each deployment of our applications to each environment to be the same. And there are some components in our system or within the MB Precise plugin which helps to maintain consistent deployments and helps to make code units and deployable artifacts as consistent as possible. And last, what we're going to do after demonstrating the SonarQube plugin, we're going to talk about the automate diagram generation, which is a feature we've added a few releases ago, which hopefully helps teams to understand their code better, and helps architects to understand what the code's doing from a more global perspective rather than looking into each individual piece of code. So if there's no questions, I'll just move on. So I'll just jump into the SonarQube console here. So this is SonarQube. We have a couple of demonstration projects, but this is SonarQube. Essentially, our product, MB Precise, sits within this SonarQube ecosystem. So SonarQube is a combination of a database and a front end. And the database captures, or the front end captures and records what we call metrics and issues, and they get saved in the database, and then another front end reads back those metrics and issues and presents them back to the user in a dashboard style format. So in this way, we can see at this point in time where our code quality issues are, and then also, because it's collecting these metrics and violations over time, we can look at the quality of our code over a period of time, not just a single point in time, not just a single snapshot. So the first thing I'll quickly talk about is metrics. So what we've developed here is a number of message broker and data power and it's doing integrated specific metrics for various reasons. So the number of nodes is just telling us how big, how big our project is. Input nodes and output nodes, HTTP nodes, SOAP nodes, are all just additional metrics we've put in for customers because they have a particular coding style, and more often than not they're using one particular type of input over another, so they just want to know when new inputs are introduced, which aren't quite within the patterns that they've developed in-house. This one here, RCD nodes. So this is an interesting one because this is RCD nodes are one of those things that have a potential to be quite compute expensive. So we're just tracking them here as its own metric, just so that teams can keep an eye on how many are being introduced or how many are being removed as part of the development process. This one here is also to do with performance, is the flow length. So what we've done here is we've just got a summary of the path through our flows. In this case here, what we've said is our backlog. I'll just see if I can open a toolset here. What we've said here is our backlog to should have reply message flow is actually the longest chain, longest chain of message flow in our system with a length of 4. So what this means is that the longest path that any message can go through the system is 4 nodes. So this is telling us what is most likely to be this is telling us what is most likely to be our most expensive computing, or potentially our most expensive computing node. And so we want to keep a track on our flow lengths, because if it's a flow that's called regularly, that's something we might want to look at redesigning to make it a bit more efficient. So I'm just going to bring that up. Backlog to should have reply. So what we've seen here is, and this is, we've just brought the same flow up here, backlog to message reply, and we can see here, yes, that the longest path through the code is 4 nodes. There's a few other metrics around here around complexity. So what we're trying to do with complexity is we're trying to measure our complexity and identify which parts of our system are most complex. So this allows us to tailor our unit testing and our testing to make sure that they're covering our most complex pieces of code, and also helps developers to address where code potentially might be more complex than needs to be. So whether they can structure it slightly differently, so it's not as complex. And when we look about complexity, we talk about in this case, we're talking about psychometric complexity. So psychometric complexity is measuring the number of paths through the code. So if we look here, this particular piece of SQL is a complexity of 30. So what this saying is in the combined different modules in this particular piece of code, there's 30 different paths. So what we can see here is there's a main path for this particular method, or this particular main, which comes through here. There's one alternative path that we might need to test here. There's a second alternative path that we might need to test here, and a third alternative path we might need to test here. So we can see a number of permutations through the code that might happen. And we have with a while statement, we have a fifth path, and with an additional nested if statement, we have additional paths. So this is saying that this is quite a reasonably complex piece of code to test, because there are a number of paths through the code that the execution will run through. So the last two we'll look at here is string manipulation load. So this is talking about how much string work our ASQL functions are doing, or ASQL code's doing, and this is important because string work is potentially CPU expensive. And coupled with that, we have something called a weighted string manipulation load, where there's a subtle difference between the two. The first one is just a count of the number of string functions, while the weighted string manipulation load attempts to give weightings to each of those functions where they're existing within a loop, or within in some sort of looping condition, with the expectation that something that happens within a loop is going to be more costly than something that happens just in a simple flow or a simple path. So that's the metrics. If anyone doesn't, does anyone have any questions? If not, I'll move on to issues. So issues is where we're talking about the find bugs or the PMD part of our plugin. So the issues are looking for common or potential coding problems, performance problems, or deviations from standards. So if we look here under our rules, now this is all the coding rules that have been implemented for Message Broker, Data Power, and Sterling Integrator, and there's quite an extensive list. And we won't go through them all at the moment, but we'll just have a quick look at the ones that have been reported. So, for example, so in this case here, we're saying we've got 251 issues. Oops. With 251 issues, which is more than what we had when we run previously, because we might have added some more code into our demonstration code set here, or we've changed some code. Now each issue is associated with a rule, and the rule can be either turned on or turned off, which means that if it's turned off, it won't get reported. So there might be coding standards you're interested in, or practices that don't apply. And also, when is there a rating. So we'll look here. So how important a particular issue is. So if something might be just informational around comments, or something that major might be something related to performance or a potential bug. So in this case here, we flagged copy entire message and filter nodes not modifying messages cannot modify the message as critical, because they both potentially cause copy entire messages is going to hit us performance-wise if we're doing extra work, and filter cannot modify the message is going to give us logic errors. So what we can see here is if we go into our exception, we can see here that somewhere in here with a filter node, which is we're saying we've got a filter node that's potentially changing the message. But in this case here, it might be actually a false positive, because it looks like even though we've got a filter node, it's actually got some code that's not being called. So we might just jump back there and just go back to our a list of issues and find another one. So for example, here we've got input pass time is not set to complete. So what this rule is saying is that for all input nodes, we want to assign oops. We want to say that all input nodes should have the pass timing set to complete. So I'll just see if I can. Okay. So we're just saying here in the code, there's an input node, and the passing is not set the way where the rule is stipulating. So we're saying that it's a violation. So what I might do is find input node domain. So in this case here, we've got node refers to an empty main method. So in this case, we've got a message flow that calls a ESQL piece of ESQL, and the ESQL itself doesn't actually and it looks like the ESQL compute node actually has no code in it, so it doesn't serve any purpose. So it's something that we potentially could remove, either for performance reasons, and so we should remove it, or we need to complete the code because it has never been completed. So for example, here we've got a whole bunch of rules around some ESQL. So we've said here that the schemas should ESQL should set the schema for each file. Each file should contain some sort of header. The header should contain something about the company that belongs to, and the header should there should be some sort of comment about what the function of the node is, or function of the code is. And then, as I said, we've got copy entire message and copy header, copy entire message and copy copy entire message and copy heading message, and then also we've got the code saying just return false. So it looks like this node basically does nothing. So in that case, we'll something that could be removed. So you get the idea of that there are a lot of violations that we're looking at, a lot of coding practices we're trying to enforce. So we'll just might quickly look at go back to our rules and just pick a few of the interesting ones, just to see if we can show them showing up. We're using cardinality within loops. It's a fairly bit of a default one. So we look here, we've got a demonstration, our demonstration project here. We've got this particular issue. Happening once. So we've got a loop, and in that we've got the we're recalculating the cardinality each time, which is a bit of a performance no-no. So yeah, so something we want to address. Okay, so that's issues. Next one I'm going to look at is code coverage. Duplications. So there's a little bit of there can be a few red herrings or false positives for this, just because the nature of the way the SQL code is written, with a lot of code actually being duplicated by the toolset itself. But this will give you a bit of an idea. So reading through this report, you can't automatically assume that everything that's duplicated is bad. Just sometimes it's the way the code works. So, for example, here it's flagged that the copy message header and copy entire message is actually a piece of duplicated code, which we're kind of expecting because it's we know that does occur in different places. But what we can do is go into one of the more other ones, and this one. And we'll look at the duplication here. No, that's not very useful. So we'll just have a quick look at one of our more complicated demonstrations. We'll look at our duplications, and we'll just see if we can find something. Okay, so what we can see here, this particular function, okay, calling a function is not very useful. Okay, we'll see here this particular declaring this particular setup, where we're creating a whole bunch of elements in the body and elements in the header of a SOAP going message, is code that looks to be duplicated. So it's potentially code that we might want to separate out into a common function. Potentially with passing in an envelope reference to the envelope outside the SOAP in the contents of the SOAP message. So we can see here that so 393, which is the line we're looking at here. So we're looking at 331, and we go down to 393. And we see the same, looks like the same piece of code's, whoops. 393 looks like the same piece of code's duplicated there. Creating creating new children in the domain, and we can see down here it looks like the same similar piece of code is duplicated again. So there might be some definitely some places we can refactor that code to remove some commonality. So that's code duplication. Now the last one we're going to look at is unit test coverage, which is one of the more newer features. So the unit test only covers ESQL and message flows at the moment. So we don't have coverage for map files and style sheets, but it's definitely something that's on the backlog. And essentially what we've got here is a report of a recorded report of which parts of our code are being tested. So we can see here that this particular filter node is being executed. This particular staff to test range module is not covered by the unit tests, or not completely covered by the unit tests. We can see that one condition with this in this particular code is covered. So this particular if condition here is being tested, is not being tested completely by the looks of it, because that if part is being tested, but it looks like the else is not being tested. What am I saying here? Cool. Yeah, so that's the test coverage for ESQL, and we're also looking at the message flows. We can see here that so what this is saying is that we've deployed the flow into a broker. We picked up that as part of our instrumented bar file, and that's how the coverage works, by instrumenting the bar file that you previously built. and then deploying it to a test environment, and then running your tests, which we can show you the end script for in a second. So essentially, this looks like it's been deployed, but it's never been hit. And just for some background here, this is the particular end script we're using. So essentially, the end script essentially the end script, let me have a look, does an init, which does some sort of cleaning up. Then what we do is we build the bar as we normally would. We've got a specific Ant task here, which we developed called instrument bar, which essentially unpacks the bar that's been built as source code, instruments, the message flows, and the SQL files, and then repackages them together. Keeps the original and makes changes to a modified version called instrument. Then, or the appends instruments into the name of the bar being deployed. Then we deploy the bar, and then what we do is we run our tests, and then we create we've got something called a stop point that essentially takes our results in memory and dumps into what we call a coverage file, and the coverage file comes out looking like this, which we then go and tell our project about by setting the generic code coverage report path to. So that means so I can pick it up and merge the coverage report with our source code and give you that red and green that we saw. Okay, so that's the first part of the presentation. So metrics, violations, code coverage, and duplications. So the next few minutes of the presentation, we're going to be talking about the automatic generation of diagrams. So a little bit of background for this, because the way the plugin has been developed, it pulls apart all the ESQL and the message flows and the map files and the style sheets, massages them together and builds up a model of how they're all interconnected, so they can do some cross checks, making sure the message flow, whatever the return result of a compute node makes sense, is consistent with what's on the message flow. So if you have a message flow compute node that has 3 returns, but there's only 2 possible returns from the compute node ESQL, then you've got a mismatch in logic and you've got a potential bug. So you could potentially get messages going nowhere. So we take that information and we generate into a HTML page that people can people and teams can distribute either as a zip file, or they can put it up on a web server, or via WebDAV or SharePoint or Confluence or some tool like that. So what we do here at the end of running our analysis, we generate our diagrams out into something called the diagram output. Essentially here, I've just set it into my local C drive. And what I've done is I've set up a Mongoose web server, just pointing to, that C drive directory, which is now publishing out this particular page here. So if I just go into the demos, this is the most recent one I've run. And what we've got here is a couple of things. So what we've done is we've report about, or we've worked out which message flows we actually have in our code, and we've drawn a little diagram for a little square for each, and then clicking on the diagram gives us a little bit more information. Looks like it's got some comments. It allows us to export as a JPEG, and shows us the how it's triggered. So we can see here that this particular one is triggered by running a queue, running a message to queue MQ_test1, which we can sort of guess here from, because we've got a queue on a purple blue queue on the top left-hand corner. We can see here that this particular flow here, this message flow here is being triggered by someone making a HTTP or SOAP request to test3, and that will trigger this particular flow, which you can see there from an S in the top right, in the middle, and so on and so forth for the flows we've got. What we can see here is you've got a flow that has 2 potential inputs. Oh, it's a bit embarrassing. It's only showing 1, so I'll just check that. Make sure the right one. Okay, so that might be oops, I'll just refresh it. So we've just pan and scrolled, so we can pan and scroll for when we have large diagrams. So that's the basic outline of the flows we have. Now, what we've done here is we've got a couple of extra checkboxes that gives us back a little bit more information about what our environment looks like. One is the tested workflow. So what we're doing here is we're taking our coverage report and telling us which ones of our message flows have actually been executed as part of our testing. So we can see here that there's only one flow that's actually been run. That's the test4 log. The other message flows have not been triggered as part of our testing that we'll be doing at the moment. So this is something useful for developers. Well, hopefully telling us that changing color. Whoops. So it's telling us that this is the only bit of our code that's been tested so far. So we might want to look at see if we write additional test cases, additional test harnesses that execute the rest of that code, if we are looking for 100% coverage. The next bit of information here we've got is a bit of a summary around the execution group. So what we've got is a little Java piece of code that attaches to your message broker that's running and extracts out an XML configuration file of or an XML runtime file of all the things deployed to different execution groups within your broker. So what this means is you can take a snapshot at some point in time of what's actually deployed into the environment, so that you can see what's actually physically been deployed. And we merge that information with the overall source code, and we can see here that we've got an execution group with nothing in it, and the rest of these execution groups have a number of flows, except for C in execution group 2, which has none. And just on our diagram, we can just turn some things on, so we can see here that this one here, we can see here this one here is the only one that's got the only one deployed in the execution group. And then we can see in, for example, this one here, execution group 4 has all those flows. There's any counting too. So what we're seeing here looks like, so execution group 4 has got 3 flows deployed, but one of those flows isn't actually from our source code. So we haven't been able to diagram it here because it's potentially not something that we've actually got control over. And the last one here was saying that that same flow is also in that execution group. Now this by itself doesn't add an additional piece of value, because this is a fairly simple demonstration diagram. But if we look at one of our other diagrams, if we look at another diagram which doesn't have code coverage, but doesn't have code coverage attached to it at the moment, but is quite a bit larger. If we look at the diagram generated and interactions, so if we had an environment that was a bit larger, and we actually had a combination of that red and green for tested and not tested in the execution groups, we'd actually be able to see here which parts of our system are actually communicating with parts of the system in a completely different execution group. And so from there we might decide that we want to couple those components to the same execution group, so there's not as much time spent switching and sending messages essentially out to other processes. Or we might decide the exact opposite, that we've got some fairly large, bulky processes that a lot of different subflows or different flows interact with, or send messages to. So we might decide that needs to be separated out into a completely different execution group. It just depends on how our architecture wants to work. But hopefully the diagramming component and the interaction component gives you an idea of what parts of the system talk to other parts of the system, how they're deployed. How they're deployed, what they're doing, whether they're consuming messages, producing messages, consuming SOAP messages, or producing SOAP services, and that gives you a bit more of and the ability to improve your deployment architecture. So the last bit of our generated diagramming is a bit more of an overall summary. So here we've got a summary of all our different flows, and we might just go back to our original demonstration project. So it gives us an overall summary. So we've got that diagram of flows, and then from there we've got a summary here. We can say this particular execution group is, or this particular flow is deployed into 2 execution groups. This particular flow is not deployed anywhere. We can do it by a queue. So we can see that this particular queue interacts with this particular flow. We can see here that we can look at where the product is actually going to and from. So in this case here, we can see that the interactions on this queue are all only within Message Broker. Now, if we had Sterling or Data Power code that we were analyzing, and Sterling or Data Power was reading or writing to those queues, we would see yes and we would see yeses and nos here. All SQL statements is where we're attempting to pull apart the SQL that you've embedded in your message flow in your nodes or in your SQL or your map files, and then we publish it here. So with the intention that it's something that we can take to DBAs, or DBAs can keep an eye on, and so they can look at the types of SQL that's being run. You're probably first thing you say is, well, the DBA can see that once you start running projects. That's true, but the other flip side of that is you might have code that doesn't get run very often. And the reason it may not get run very often is because it might be fairly large and batchy, and doesn't need to be run except fairly rarely, but it might be doing a lot of work. So those sorts of queries the DBAs might not see in their analysis of their daily logs or the daily statistics. So they're looking at the fact that it can execute and what it will do if it is executing. Data sources properties, just looking at what's there as far as what's in the flows. Common ESQL methods, so essentially we're looking at things, pieces of code that don't really attach to an individual filter or node, and they're more schema-wide. So in this case here, we've got some generic sort of schema code that might be called from other places. So it helps to build up a sort of a library of code that can be used by other developers. More common code. We just listed all the Java codes that are being used from ESQL, looking through the stored procedures, the events, files being read by Message Broker, and files being output by Message Broker. And this sort of ties into our discussion around execution groups. So one of the things we are looking in the future is to write some more rules around, once we've discovered what execution groups there, we might allow architects to add some configuration information to each execution group to indicate what sort of things it's allowed to do. So in the case of execution groups, it should or should not be able to write to the file system, with the intention that, the thinking that you need hidden privileges to write to the file system. So you may want to limit that to only one execution group that needs to be started with that particular hidden privileges. And then also, from an architectural perspective, you might not want each and every execution group right into the file system, because you might end up producing file contention because you've got two things trying to read the file at the same time. You might have duplication processing or cause other issues. Input URL. So these are all the URLs. These are all the URLs that brokers producing services for. So we can see here these are the essentially the endpoints that brokers serving up, and so we can see here that that doesn't seem to make a lot of sense. So there might be some actually configuration issues where we've got the same URL being providing services for or providing services using two different flows. That does make a lot of sense. So it looks like one of these flows actually may be duplicated, or one of these URLs isn't correct. The output URLs. This is where our message broker is consuming a service to someone else, so we can see where it may be going to another broker, or it might be going to another component, or it might be going to a third party. Throwing exceptions just helps us document our exceptions, so we make sure trying to get a bit of consistency around it. Data power, input and output URLs, Sterling, and these are Sterling specific sort of reporting. So that comes to the end of our presentation. We'll just stay on for next minute to see if anyone does have any question. And if not, thank you for joining us. If you do have any questions or you will need any clarification, please drop me an email or send me or jump onto the Zendesk chat off the website, and we'll try to answer the questions or any questions you have. We'll end up finishing a few minutes early, which is always good. So if everyone can go finish their coffee or start their working day. Thanks again for joining us, and I hope you got something from it.